All right, this last video on logic is going to cover negation of quantifiers as well as nested quantifiers. So negating quantifiers. So let's think about this right here. Every student in this class has taken programming fundamentals. Now, this is a universally quantified statement, so we can express it as for all x, p of x. All students in the class have taken programming fundamentals. There's p of x has taken programming fundamentals, and the domain is all students in the class. This isn't true, right? Many students in this class have taken programming fundamentals, but not all of them have. So this statement is written, this is a false proposition. This is a false, universally quantified predicate. Okay, so that means that if we look at this proposition, this is true. It is not true that every student in this class has taken programming fundamentals. An equivalent way to write that is this. There is a student in the class that has not taken programming fundamentals, which gives us this existentially quantified statement or proposition. Now, I want you to look at this. Our original proposition, our original quantified statement was all x p of x. That's false. Remember, if you negate a false statement, you get a true statement. This true statement. So that gives us this expression. This tells us how to negate a universal quantification. The negation of for all x p of x is saying there exists an x such that not p of x. And that is the first of the next two set of DeMorgan's laws. DeMorgan's laws with quantifiers. Remember, we had DeMorgan's laws for or statements and statements when we just had propositions. Now we have DeMorgan's laws for quantifiers. So they tell us how to negate quantified predicates. So the negation of for all x p of x is there exists an x such that not p of x. The negation of there exists an x p of x is for all x not p of x. So the way I want you to think of it is kind of like this. So if I write not for all x p of x, this is equivalent to the negation turns my turns my universal into an existential. And then that negation kind of moves over to negate whatever my original predicate was. That's how DeMorgan's law works. If you want to negate an existential, the negation turns the existential into a universal, and then the negation kind of moves on over and it negates whatever your predicate was. So for example, someone in the class can speak Latin. Well, that is saying there exists an x such that L of x, where L of x is x speaks Latin, and its negation would be for all x not L of x. Okay, so that's because not there exists an x L of x. The negating the existential turns into a universal. Then a negation moves over to get not L of x. That is, all students in the class cannot speak Latin. Okay, so here's an example that we're going to do. Find the negation of the statement for all integers x squared is greater than or equal to x. Well, this is in symbolic logic for all x. We'll write this as p of x, where p of x is the statement x squared is greater than or equal to x, and the domain is the integers. So if I'm going to negate for all x p of x, that's equivalent to saying there exists an x such that not p of x. In English, that would be there is an integer such that x squared is not greater than or equal to x. And then you can go ahead and rewrite that one more time and say such that x squared is less than x. That's how you would do that example. Now, we can do this with compound statements. So consider this. Some dogs are big and fluffy. We can write this as there exists an x such that b of x and f of x, where b of x is big, f of x is fluffy, and the domain is dogs. So saying some dogs are big and fluffy is there exists an x such that b of x and f of x. So how do you negate it? Well, I'm going to do this step by step, but here's the punchline, right? This is the answer. But let's just see how all this breaks down. So there exists an x, there does not exist an x such that b of x and f of x. Well, how do you negate this existential? It turns into a universal, and then the negation moves over, and I'm negating this and statement. So this first equivalence comes from DeMorgan's law with quantifiers. And now I have to negate this, but I'm negating an and statement. So I'm going to use DeMorgan's law for propositions. So this would be logically equivalent to for all x. So how do you negate an and statement? Well, it turns into an or, and then you negate both parts. And so in English, that would be for all x, not b of x or f of x. That is, for all dogs are not big or not fluffy. So that's how negation works for quantifiers. So now let's move on to the last thing I want to cover out of this section, which is nested quantifiers. So this is when you want to have more than one quantifier under consideration for a given proposition. So think about this statement right here. For all integers x, so that'll be my domain, there exists an integer y such that x plus y equals 0. So here's my domain for all integers. I have a universal quantifier and I have an existential quantifier. I have two of them, okay? And then here is my, here are my two variables, my two predicate statements. So what I'm saying is for all x, there exists a y such that s of x and y, where x and y are integers, and s of x and y is this proposition, the one that I had there. So what this is saying is, think about this. I'm saying for every integer x, I can find a special integer y that makes this predicate true, x plus y equals 0. So for example, if you have an integer, say 5, then you can find an integer y, which in this case is -5, that makes this proposition true. The order of the quantifiers matters. This one would say there exists an x such that for every integer, x plus y equals 0. That one's going to be false, because in this statement, you would find an integer so that no matter what you add to it, you would always get 0. So the first one is true, the second one is false. So the order of your the quantifiers is very, very important. It can totally change the meaning of your statement. So here's some examples. I'm not going to work these out because I want you to have some things to practice, but also there are some from the practice problems that I do want to work out. Okay. I do want to talk about negation of quantified statements. So if you want to have something like this, the negation of for all integers x, there exists a y such that x equals -y. Using quantifiers, we could write it like this, where n of x is the proposition x equals -y, and the domain of x and y is the integers. So how does this work? Well, if I want to negate for all x, there exists a y such that n of x and y. Well, DeMorgan's law tells me this universal is going to become an existential. So for all x, not there exists a y such that n of x and y. Now DeMorgan's law tells me that negating this existential becomes a universal, and then I have not n of x and y. So it says that for all integers x, it says there exists an integer x such that for all integers y, x is not equal to negative y. So let's look at the notes. So here's a set of notes for nested quantifiers. So lots of examples for you to read through and kind of unpack here, which is important for you to work on. Again, I have some videos for you to watch. Please do that. And then we have the practice problems, which we're going to do in just one moment. And then in the one on negation, again, read through this, watch the videos, understand these examples, and then try these practice problems. Speaking of practice problems, let's do some. All right, so Q of x is going to be the statement x times y equals 0. The domain for both of them is going to be the integers. What are the truth values for the following? So I'm going to do B, and I'm going to do D, and I'm going to do E. Now, when you do these, pay particular attention to what you get for F, because the difference in E and F is switching the order of the variables. So just think about that when you do these. So B is just saying, so Q of 6, 2 is just saying 6 times 2 equals 0. Well, that's false, because 6 times 2 equals 12, which is not 0. That is a false proposition. Now look at this one where it has been quantified. There exists an x such that Q of x and y, Q of x and 4. So this says there is an x, an integer. Remember, these are all integers, so that x times 4 equals 0. Well, this is true. Just let x be equal to 0, because anything times 0 is going to give you 0, and 0 is an integer, so that one's true. And then for E, we're going to have for all x, there is a y, so that x times y equals 0. So when you think about this, here's what you want to think about. X is the one that can vary, okay? So it says no matter what value of x I pick, there is a special y that when I multiply it, I get 0. Well, this is true. Just take y to be 0, because now for any x that I pick, when I multiply that x times 0, I'm going to get 0. Again, it's important to think about the order. For all x, there is a special y that's going to be true no matter what x value you pick. So when you practice these and work these problems out, write this out in English first, which I always encourage you to do, and see what happens when you switch the order of your quantifiers. Okay, moving on to the next problem I want to do. Let's look at this one. Find the negation of these statements. I'm going to do B, okay? The light is green, so we can go. Well, this is saying that if the light is green, then we can go. Now, I haven't mentioned this yet, which is why I threw this example in with these. This is a conditional statement. This is an implication. This is saying, I'll tell you what, why don't we just let the light is green? That will be the proposition P, and we can go be the proposition Q. So this becomes if P, then Q, or written another way, P implies Q. Now remember implications, okay? The truth table for an implication looks like this. here's true, 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 false, false, true, false, false. So this is true, true is true, true, false is false, false, true is true, false, false is true. The only time that an implication is false is when we have true implies a false. That is when P is true and Q is false. So that tells us that the negation of P implies Q is when P is true, so I have P, and Q is false, so and not Q. So that is how you negate an implication. This is an important thing to remember, okay? That this is how you negate an implication. The negation of P implies Q is P and not Q. So going back to this original statement, I'm going to write it right here. The negation of this would be P and not Q. So the light is green. That's P. And we cannot go. So think of it again in terms of when are you being told a lie. If the promise you're given is, if the light is green, then we can go. Well, that is a lie when the light's green and you're not allowed to go. So that's how you negate implications. All right, moving on to this last set that I wanted us to look at. Well, the second to last set, I also have those. Find the negation of these statements. I'm going to do C. No monkey can speak French. So there does not exist an X such that f of X, where f of X is going to be X can speak French, and my domain is going to be, I guess we could pick animals for our domain. But this is the quantified statement. There does not exist an X such that f of X. Okay, actually, I think the domain should be monkeys because that's what the specific thing we've plugged in there. So negating this is logically equivalent to, DeMorgan's law tells us to move that existential to a universal and then negate the predicate. So in English, this would be all monkeys cannot speak French. So that's how you negate that. And then now moving on to the real last set of problems, we have some statements using quantifiers. We want to form the negation and then write the negation in simple English. So the first one is, every student in this class has taken 2 math classes at this school. No one has climbed every mountain in the Himalayas, and there is a student in this class who has never seen a computer. We're going to just do part C for this one. So there is a student in this class. We could write that as there exists an X who has never seen a computer. So the way I'm going to write this is, there exists an X such that for all X, S of X and Y. So what am I saying here? X, the domain is going to be all students. Y, the domain is going to be computers. And then S of X and Y is going to be X has seen Y. So saying there is a student in the class who has never seen a computer, I would have to put a negation right there. So that for all, there exists a student such that for all computers, the student has never seen a computer. So the negation of this would look like what? The negation of there exists an X such that for all Y, not X and Y. So DeMorgan tells me to flip this existential into a universal. Then that moves over. So I flip the universal to an existential. And then that turns that negation, it's a double negation, so it goes away. So this is what I have. For all x, there exists a y such that x and y. So in English, this would be, for every student, there is a computer that the student has seen. So in other words, every student has seen some computer. And that's how you would not only write the nested quantified predicate in English, that's how you would negate it and then translate it back into English. So practice these problems. And as always, let me know if you have any questions whatsoever.